Hello, everyone. Good afternoon, good evening, depending where you are. Typically, I get to do these webinars from the States where I'm from, but I have the fortune this week of being in the Redgate office in England. And so it's been a good week so far, talking with the product teams and talk about what we get to do with Postgres here at Redgate. So thank you so much for joining us. I'm going to talk today about Postgres indexes. And, as we continue to see more and more people adopt Postgres, all of the things that we have come to know and learn about databases, particularly those of you coming from something like SQL Server, the nuances of each of these things are so, so familiar to us, like indexes. But those little nuances and the things that will ensure that your queries and your data continue to work well or potentially regress from what you would expect. And so, in this short webinar today, about 30 minutes or so, we'll talk about the kinds of indexes that Postgres supports and a couple of the nuances of what you have to think about as you prepare to begin to use more and more of Postgres and the indexes. So my name is Ryan Booz. I am a Postgres and DevOps advocate here at Redgate. You can contact me on social just about anywhere with Ryan Booz. That's X or LinkedIn. Softwareandbooz.com is my blog. At times we'll throw some new stuff up there as I'm learning to try and help others learn too. So please reach out and don't be afraid to ask for some help or suggestions as you're learning. So today, we did a lot of these Postgres 101 series last year, and we've had a busy year doing more and more with Postgres and the tools here at Redgate. And we are beginning to come back around and recognize that there are still some subjects that we didn't cover as we did these last year. And so this is the first of 3 for the rest of this year that we're going to cover. And so today, again, we're talking about indexes. If you have not seen these before, if this is the first Postgres 101 webinar you have attended, please feel free to look at this website. It is kind of our landing zone for all things Postgres content-wise here at Redgate. And then we do have a playlist, and you can find this and other webinars and videos and educational content at Redgate's YouTube channel. Couple quick things as we begin. So this is being recorded, and you will get a shared link of the webinar to watch again and share if you need to. So go ahead and pay attention as much as you can. Don't be concerned about taking notes, things like that. Just take in what we're going to talk about today with Postgres indexes. And if you have questions as we go, please use the Q&A box in the webinar framework that you have, and the team will get them to me. We'll answer those at the end as we go. So just as we're going, you have any questions, throw them in there. So we're going to go ahead and dive right into Postgres indexes. So if you're coming from a different database, often, again, at Redgate, we have a lot of association with the SQL Server community. And so we know that a lot of folks are learning Postgres new. A lot of companies are asking their teams to consider it for new projects or potentially even move existing projects to Postgres over the next few years. And so when it comes to indexes, you need to know that there are things that are the same as what you expect. So by default, when you create an index on a column, it will be a B-tree index. That stands for balanced tree. Now, that's just standard among relational databases, and that's generally what you would expect. Now, in Postgres, again, we also have support for multi-column B-tree indexes. You can do partial indexes, things that are filtered, an index where you set some kind of where clause that dictates what's included in that filter. It can be really powerful depending on a specific data type or data distribution. You can do covering indexes. So those would be indexes with included columns. And you can also do computed indexes. So you can have an index that is based on a function output, something that is computed. And again, that can be very helpful depending on the data that you're indexing and what you need to do. And a simple example might be you need to lowercase an index because you always compare against some form of text in lowercase. And again, whether that's your situation or not, that would be an example of an index on something that's computed over time. And then SQL Server does have some spatial capabilities. And so there is actually spatial index. And as we'll learn throughout the rest of this presentation, Postgres has many different types of indexes and the ability to create some new ones. And so PostGIS is an extension for Postgres. We've talked about extensions previously in other 101 series recordings. And PostGIS really has become the standard in relational database spatial data management and querying. And so with PostGIS specifically, there are a number of unique index types created for spatial data with new spatial data index types that you can add to columns and so forth. So we do have that as well with the free extension. And again, that extension is available really anywhere you can use Postgres, even in the cloud and the providers that you can host Postgres with. A couple of things that are different that just come top of mind, and this is often a surprise, again, when you're coming from something specifically like SQL Server. First, there is no such thing as a clustered index in Postgres. Now, there is a clustered command which will essentially do the same thing, but it's a one-time command. And so every time you cluster a table, it will reorganize the table by the clustered column. However, as soon as data is updated or inserted, it is no longer in clustered order. So nothing about Postgres, we just don't support clustered indexes. And that can be really interesting and challenging to think about because so much of how we have been taught from a SQL Server perspective to interact with and think about our tables and how we organize the data and index them has often been really centered around the clustered index, what that will be to help keep the order of our data on disk, both for the benefit and sometimes for the challenges that it provides. And then the other thing is we do not have a column store index by default. Now, my answer to most things when someone says, does Postgres support this? And I have to say no, not natively, not with the generic, out-of-the-box Postgres that you can get yourself or in hosted environments. But as with most things, and again, I'll point you back to maybe we'll include it in the notes, the webinar we gave about extensions. There is an extension, or there are actually multiple extensions for doing column store and column store-like indexing in Postgres. But out of the box, we do not support a column store index for your data. And then the other thing to think about, and I put a little asterisk here because I'm going to revisit this very briefly at the end, is that all data, because we don't have a clustered index, that means that all data for all tables are stored as heaps. And that, again, can be really a new way of thinking about how data is accessed because you don't have control, particularly when it comes to things like table scans, how the index scans are used and some of those things. And so we're going to revisit that really briefly at the end once we've looked at all the index types, because it will begin to impact how you query tune. And and as you learn more about query tuning in Postgres, which we aren't going to cover today, you'll start to understand why you see things like table scans when you may expect indexes to be used and some ways to overcome, when that happens and you don't expect it. Now, I would say a couple of things that are better in Postgres out of the box because of its open source nature are things like with indexes, you can concurrently create them, you can concurrently reindex and drop. Now, this can be done in other databases, but it typically requires some kind of license upgrade. Creating, in this case, like an offline index in SQL Server, so it's not impacting, it's not taking that exclusive lock of your data. This is something all index types support. When you reindex, and even when you drop an index, you can do that in a way that has less locking impact over time. Number two, Postgres by default, out of the box, supports 6 different index types. And that's what we're going to cover today. And that might be a challenge to think about, right? We're so used to B-tree and column store indexes when we come from SQL Server that even to think about what those other indexes might be and how they might be beneficial, hopefully you'll see that by the time we're done here and begin to see that there's really an interesting way that Postgres, those that are developing extensions, can use some of these frameworks to create really unique and helpful indexes for new data types. And that really points to the third bullet here, which is because Postgres provides this generalized framework, as new data types are created, whether it be something like geospatial, even something like indexes, like images, we could create a unique index over each data type that we provide for some new reason in our application that we need to store. And so we'll get to that in just a little bit. So those are a couple of the a couple of things I would say are quote unquote better and just new things to be aware of as you come to Postgres. So the included index types, when you install the core product, so if you were to download and run, say, the Docker image, or maybe you compile Postgres, or you're on Linux and use an RPM, something like that. Even if you use Postgres in a hosted environment like Azure or AWS, these indexes will all be available in some form or fashion. Now, the 5, actually 6 on the left, are always available all the time. They won't be taken away. The 3 on the right are available with an extension, but all of those extensions come included with the base package of Postgres. They just aren't installed by default because they do take some extra effort. They are actually a little bit more management heavy and intensive. And so the core team, as they develop Postgres, they want to make sure that you make that choice to enable an index type that might take more effort, might take more resources. It can be very, very helpful. Trigram index can be really cool to use and can actually solve some problems that are difficult without that index. Now, but it does require more maintenance. And so again, they want you to choose to install that extension so that you know what you're doing and that you're gonna take that overhead. Otherwise, out of the box, we support btree and we support gist and spgist. We'll talk about briefly as we go. Gin indexes, Brin indexes, and finally hash indexes. So without doing anything, if you have access to Postgres, you have access to these 6 data types. So let's start from the top. First, we have btree indexes. Now, if you've been using a relational database for any length of time and you've created an index, this is most likely what you have created. And if you've done any kind of learning, even been in school to learn about databases, you know, the balanced tree index is kind of the standard. We start at a small set of pages of data and references, and we slowly fade out, leaf out through a tree. That's the visualization we use. And the leaves of your index point to the data pages of the data. And so it's really what you would expect. It's a classic btree index. This is the default index type. If you just create an index without identifying a different type, this is what you'll get. And it can be used for all of the traditional operators, the predicate operators in a where clause that you would expect: equal than, greater than or equal, between, like. All of those things can be used with the traditional btree index. Their efficiency might not be exactly what you need depending on what the data is and how it's indexed, but they can be used for all of the typical where clause predicate operators that you would expect. Now, you cannot index composite types. So Postgres supports some additional data types that we've talked about previously that SQL Server and others do not. Things like arrays. So you can actually store arrays in a column as a unique data type. Every single data type in Postgres, ints, text, booleans, any of them can actually be represented as an array. And so btrees cannot index arrays. You just won't get the value out of it, and therefore it can't be done. Actual JSON data type, you cannot index with a btree index. Now, one of the neatest things that's happened over the last couple of years in Postgres with the btree index is an improvement that was made in optimization in Postgres 13, where now btree indexes can be deduplicated. Now, what does that mean and why is that valuable? And that probably should have been in the better column of the last slide. So in a typical btree index, this is a really simple representation. The top is the index, and you'll see that it's ordered. We would expect the btree index to be ordered in some fashion. Now, I'm not showing this as a tree. This is kind of the end leaf pages, as it were. And every leaf page points to a row somewhere in a page of data, right? So the data itself is a heap. It is not guaranteed to be ordered. But the index is, and it kind of points across all the pages. However, what was done, there's this optimization that takes place when you re-index, or anytime that you need to insert a new value in the middle of an index, which might create a page split. So this gets into the nuances of the page level of how an index works, which is not the intent of this specific talk. It's more database theory. But when we insert values, at some point, the actual location on disk is represented by 8K pages by default, so 8 kilobytes. And if we insert a value into the middle of that page, because the index needs to stay ordered, at some point that page gets full and the Postgres needs to split that page in half. So there's now more room to store more values, in this case of A, and more values of B within what was that page. And so to prevent splits, to try and prevent splits from happening, which is a costly operation and does incur a slight amount of locking, Postgres, the developers came up with this optimization. They said, hey, when there might be this possibility of splitting a page, we're going to do this optimization where we will simply take all of these references. And so in a regular B-tree index, there's one leaf for one representation or row of data on your actual table. Well, what if we could just take all of those row references and simply have an array that points to all of the pages that were in this index? So we go from a pretty big array, and now we can actually store more values within that AK page. So now we know that we are indexing the value of A, and it can point to all of the page and row references throughout the database, wherever they may lie. And indexes are efficient, and they can be reused in other ways. And so we end up with this kind of free compression without doing anything. Now, again, if you upgrade from a previous version, Postgres will not deduplicate. And deduplication technically only kicks in when a page is about to split. Postgres will examine the index page, determine if it can deduplicate it, and kind of free up space to be reused again. And there's more complex things that happens here. Some reorganization of the index can happen to free up more pages. All of that is possible. But just generally, this is kind of what happens under the covers. And often you can get 30–40% compression, as it were, or savings in space out of deduplication. So if you reindex, if you upgraded from a previous version, the only way to get deduplication is to reindex. And you can, if you want, actually turn off deduplication. So it's on by default with Postgres 13 and above. But if for some reason you decide it's not helping, or there's a reason you don't want it for some specific index, you can turn it off and go back to the old way of doing a B-tree index. Every leaf node has a pointer to every individual reference, wherever it might be in the table. So that is B-tree deduplication and the basics of B-trees within Postgres. Now, the second index type that we support is a hash index. So in relational database theory, in relational databases, a lot of what we do can be done through hashes. It's a really efficient way to take a lot of data, especially data that's represented with repeated values over and over again. We can create buckets out of them with some kind of modulus. And we say, hey, we take each of these values and we're going to represent it as an integer. So, and have a method, a function that will always return the same integer regardless of the value that you pass in. So if I pass in a word, I'm always going to get the same value back for that word or that string of text. And then I can efficiently find all the representations or all the rows of that data on a page. So hashing is a really common thing that we do in relational databases, in theory, and joining, and so forth. Well, in Postgres, we can create a hash index. So we can take all the values. You could almost think of this as a dictionary kind of index. So we take all the values of a column. Let's say you have a column that has products, and that product name is repeated multiple times throughout the table. Well, I can take that product name, hash it, get a value that represents that specific value, and then just store the hash in the row pointer. So now I don't have to store the actual value, product of bike and product of baseball bat and product of, golf club. I don't have to store those things over and over again. Now, again, typically in a relational database, you would hopefully have a linking table there. But this comes to more things that might have similarities, but are not your foreign keys. So everything is pre-hashed. It's a very efficient, very small index. And then what you're storing is just a list of row identifiers. So we're not storing the actual indexed value. We're storing the hash of that value, and then the pointer to all the occurrences of the row pointers within the table. Now, hash buckets start technically as 2 buckets, but it expands over time as needed. So as Postgres hashes more values, it will create more buckets to store those values in. And again, the more densely populated you have some kind of hash values, the more efficient the hash can be stored. However, one limitation is this can only be used with equality, right? A hash is literally taking some value and it's creating another representative value out of it that's more efficient and easier to store. It's a 4-bit value always. And so we can't do, we're not storing all the individual bits of the thing that you hashed. And so equality operator is the only time this is useful. And it will require a recheck of the actual rows as the page is stored. So Postgres is pointing to the row values where they exist on individual pages within the data that's stored on disk. However, there are times where there's such an infinite amount of possibilities of what can be hashed. You will get different types of values that might hash to the same hash value. And so when Postgres then pulls the data page, it still needs to go and ensure that the row that it's pulling off of that page matches the value that you originally asked for. So there is an extra step, but again, because the hash index is so small and you're getting individual pages much more efficiently, this is usually a much more efficient, fast operation for searching for this data. So this is how you create a hash index. You actually identify as using the hash index type and then the column that you are indexing. Really, really quickly, this is kind of what a hash index might look like. So it's stored in buckets, and the values are always integers. So bucket 0 would be a hash value of 0. I took some kind of, in this case, maybe a string. I used a hashing function, and I got 0 as the hash value. And I might have multiple things that come back as 0. And so they would the row pointers for all of these values would be stored in that bucket. And then when I ask for, let's say, C8F2, it's going to go look and say, well, this bucket points to all of these rows across the database and off of all of these pages. And so it can quickly read those pages, and then it will have to recheck as it's pulling those rows off to ensure that the pointer actually points to the C8 value rather than, in this case, my D7, B9 value. Again, it still is much more efficient than, say, reading the entire table or potentially going through a B-tree index simply to get to the same pages. So it's very efficient, ends up being very, very small. And if you're doing an equality check for a specific value over and over, that is in some kind of dictionary-like form. You have multiple repetition of a value. Hash index can be really, really efficient and fast. So consider using it. Now, the next two kind of form into this, and actually next three form into this generalized index type. What do I mean by that? So a long time ago, some developers included these frameworks for creating new index types because they were creating new data types. And they realized if they could program an index to store data specific to that type, they could search it much more efficiently than, say, with a B-tree. And so that's what these next couple indexes are born from. It's from this framework. And essentially what this means is Postgres provides the functions that you need to implement as the subject matter expert, the SME. So if you create a data type, in theory, you know how to most efficiently search for that type, the properties of that data that you want to search on or that others may want to search on. So Postgres provides the functions, you implement those functions to help it understand how to index and then search your index. And now you can create an index on your own. And we have a lot of these in Postgres. There's a lot of new extensions like PostGIS I referenced earlier. PostGIS creates a lot of different spatial data types and therefore has unique spatial indexes to do things like nearest neighbor searches on a map. And so these come in two flavors, a GIN index and a GIST index. And there is what we call an SP-GIST, which is for space partitioned GIST index. That's a little bit more rare. I don't see them often in the wild, but if your use case fits, it could be something you'd investigate. And then the other really cool thing with these generalized indexes is that they do have, and I shouldn't have used the word unique here. I will have to change that for later, an expanded set of comparison operators. So it's not just greater than, less than, or equal, although it might support those, or it might not support those. You might not get equals in a GIN or GIST index, believe it or not. But it will support some other things like overlaps. if I have spatial data, I want to see where various sets of data overlap to see that they're in the same region. That's where like a k-nearest neighbor might work. Or I have arrays. I might want to see where the arrays overlap so I can find the unique values within multiple arrays, things like that. And so there are actually different operators. You'll see things like 2 @ symbols or 2 and symbols, and those mean different things depending on the data types you're comparing within your clause. So first is the GIST index. So GIST stands for Generalized Search Tree Index. It is really well suited for overlapping data. So the first thing to say is a generalized search tree index is still a tree. So it looks very similar to a B tree. It is not guaranteed to be balanced, however. It does try to stay as balanced as possible. But the idea here is that by having a tree, you can more easily find values that overlap over time and use these new operators and so forth. Now, the intermediate pages that are stored, so you start at the root of the tree, and then before you get to the leaf pages, are often bitmaps because they're more efficient to search. And again, when you're finding overlaps, you'll find bitmaps that come close to finding the pages where the data is at. These are implemented already in Postgres. By default, you can use it for full text search. GIST indexes for full text search is very efficient. It's really been utilized well over many years. So there's a lot of information out there about how to do full text search in Postgres. It's not a unique data type. There are some new functions that you can add or utilize, and then a new way to do the full text search. And so that's all supported through a GIST index. And then, as I said, geospatial is probably where this is used the most. So if you're using something like PostGIS, the indexes, most of the indexes they provide, the index types, will use a GIST index, and then you specify what kind of spatial operator, and that's the way it indexes when you create the index. So again, hopefully you see a theme. As you understand the kind of index you're using, in this case a GIST, you simply create your index as you normally would, but you do have to say using the GIST index type and then the column that you are indexing. The second generalized type, and again, these are generic types that you can program, someone can program specific implementations of. So this stands for inverted tree, so generalized inverted tree index. And that simply means we generally start with more values at the root. We're indexing multiple things and narrowing it down the further we go, rather than starting narrow and getting wide at the bottom. A little bit harder to visualize. That's why I don't tend to do it. I tend to give examples of, when I would be doing a demo of just how these work with different data sets. But it's just inverted. Think about it. It doesn't quite look like a tree. It's a little bit the opposite direction. Now, they can be maintenance heavy, but the value here is that you can do things like arrays. And again, it's really easy to look at to the left of an array or to the right of an array. So really useful, particularly as you consider new data types. Now, this is also useful for things that look like arrays, like JSON objects. And so there's a JSON data type in Postgres, and GIN indexes are really valuable for indexing actual specific values within inside a JSON object, for instance. So it can be really powerful. Common use cases, again, are arrays, JSONB or JSON columns, and range types. So I happen to really like using arrays and range types in Postgres when they are useful. And then it's really valuable to be able to say, hey, I have this range of values. Think about something like a hotel system where you need to have a check-in and a checkout date. Well, if you need to see dates that overlap, someone is searching for free rooms, you could have multiple columns and multiple B-tree indexes and have greater than and less than and overlaps, or you can have a GIN index that helps you literally find overlaps through the index rather than having to search multiple trees and bring them back together. And so really powerful and really useful specifically for unique data types. And again, out of the box, you simply have to say, I'm going to use a GIN index and know the data type. So again, in this case, maybe something like I should have put a range type in here, which is what I thought I had changes to. My apologies. The data set that I use in demos has a range type for renting DVDs, for instance, the beginning of the rental and the end of the rental. So it's really easy to find movies that are currently being rented. I just have to say, here's the range I'm looking for. anything that matches within that range is currently not here because they are on rental in some way. So again, really fun, powerful, interesting ways of indexing unique data. And then probably one of the most unique, just from a thought perspective, thought leadership almost, is at some point a number of years ago, I believe starting with Postgres 10, maybe it was 9.6, one of the developers said, what happens if we are searching for all of these kinds of data? We have a data type, and particularly because it's a heap, we have to go page by page by page and find those individual rows, and that can be really expensive. And if I'm going to tend towards data that maybe is sequential, what if I could just kind of say, let me look at larger ranges of those data pages and be able to exclude lots of pages at once. And so when you read a data off a page, I keep saying page, the 8K page of data that stores all of your actual row data, I still have to read that 8K page to get that one row value out. So if I can not read large groups of pages, because I know the value I'm searching for does not exist in that range of pages, that saves me a lot of time and I/O. And so that's what this is. By default, as you create a block range index, Postgres scans 128 data pages at a time and essentially stores two things based on the column that you're indexing: the high value and the low value for the entire range of 128 pages. You can modify how many pages it does per index and so forth. By default, it's 128. So let's say you're looking at dates. Maybe you're indexing a date column, and by default, it generally is increasing. Maybe it's time series data, and you're just always inserting new data. Well, if I'm searching for data that's greater than a week ago, well, I know that those are probably somewhat contiguous on my data pages, and I can skip all of the other data pages beforehand on a very small index. I don't have to store a really large B-tree index simply to know, well, all of those pages, way back in the past are not going to have this value because it doesn't exist between the high and the low range of that entire block of pages. And so it's similar to a hash in a way, but it's storing something that's a little bit more unique, right? We're saying for this entire bucket of pages, all 128 data pages, does this value exist between the low and the high range? It doesn't. I don't even need to look at those pages. I can just skip right over them and check the next 128 pages. And so this is really useful. They're very, very small. They simply store pointers to the block range, the range of 128 pages that you need to look at, and that's it. So data, that has natural ordering, like time series data, is really useful for Brin indexes. Zip codes, something that might increment over time, or counter values that increment over time. If you're storing something like that, again, that way we know that within a range of pages, the value exists or doesn't exist, and we can move on very, very quickly. These are very, very small. Something like this is what happens. It just looks at 128 pages at a time, simply stores the high and low value, and then a pointer to all of the pages that exist within that range. The values and the rows that exist in that range. And so if my value is below 0 or above 50, I skip them and move on. And you can see how this becomes very, very efficient. It simply points to the range of pages, to read it or not read it, or the executor knows to read those data or not. Now, I point this out because it's a unique implementation of this. And this goes back to Gin. I've used it before, and I mentioned this and a couple others at the very beginning. Now, trigram is an implementation of the Gin index. I'm showing this to you for a reason on the next slide. Number one, it's just kind of cool. It's included with core. And if you have ever heard of a trigram, it's a really efficient way to search for values of strings within the entire string. So it's good for, like, say, strings that might be 100 characters or 200 characters or less, not whole text. That would be full text search. If you're looking for, say, autocomplete of maybe titles. So in my movie database, maybe as people are searching for a movie title, I'm searching the database after they type 3 characters or more. And as I continue to type characters, I can search a combination of these individual 3-character sets of data. And that's exactly what this does. Rather than having to implement a trigram, index in your own, and there are ways to do that, This is saying take the string, index individual 3 characters at a time, the first 3 characters, then characters 1, 2, and 3, and then 2, 3, and 4, and 3, 4, and 5, and 4, 5, and 6. And that's a really cool and efficient way of searching a string. Now, I showed it to you because it's an implementation of gin, but it's not provided by default. And so if you want to create a trigram index on a string, you have to actually specify the trigram operator. And so that is the unique implementation. As I said earlier, gin is a generalized framework. The trigram developers had to implement a unique index type, and we call them operators. And so we have to specify, hey, for this text, it's a gin index of the trigram operator type. And then Postgres knows exactly what to do. As it indexes new values, it knows how to store those individual 3-character representations throughout the string. So that, by and large, is the main index types that you can use. Some of them are very space efficient. They come with some unique nuances that you'll get to learn, but at least knowing they exist, understanding that unique data types provide some really interesting opportunities, both reduce the storage of indexes, which helps everybody. It's less I/O, it's less memory storage, and those smaller indexes often create smaller read operations because you're reading fewer pages off disk. They're really, interesting in how they pull that data off. Knowing those indexes exist, though, does still provide one thing I briefly wanted to mention. Now, we're going to talk about this more in future webinars. We're going to have some resources coming out in time for PASS Summit that we're really excited to share with you that will get into more details of all different pieces of Postgres and much more detail about indexes in this case in query tuning. But knowing all these indexes exist, there's still one thing you need to remember, is that all tables in Postgres are heaps, which means indexes themselves generally are ordered, they're organized, but they might point to pages of data that are disparate all over your disk. And again, that gets to kind of disk storage layer and understanding pages of data. But heaps are random by nature. A value of A might be on data page 1, and it might be on data page 10,000 and nowhere in between. Or it might be on 100 pages in between those ranges of data pages. And that's a very random operation to go find each of those pages of data. Now, that meant something when our indexes were stored on what we used to call spinning rust, right? So metal spinning disks that were slow, particularly for random operations. And so what the developers did back in the day is they actually have a multiplier that says, hey, if this read operation from this index is going to create random reads, make it by default 4 times more expensive. And so as the cost optimizer in the plan is determining how to go get the data, it might say, hey, I know there's an index, but I'm going to end up reading enough pages anyway, and they potentially are so disparate on disk, I'm going to have to jump all over the place. It is simply faster for me to just read the table from beginning to end and filter as I go, because the randomness of getting the data is slower than simply reading the data in sequence and filtering it as I go. And so you will notice as you have to query tune into your queries in Postgres, you will often find times where you'll say, this is telling me it's doing a sequential scan, which is a table scan in Postgres, but I know I have an index on this column. Why is it doing that? Well, that often is because the cost, even though there's an index, Postgres said, you know what? From what I can determine, it is less costly to read all the data and just scan it as I go. Now, you can, this is going to happen more with smaller tables, more likely. And part of that is because the table is in memory anyway, and the effort of looking the values up and then reading the pages really is probably slower than simply just reading through those pages quickly and getting the values out. However, knowing that the default the random page cost is set to 4, that's an old value on SSD and even most modern cloud storage. A value of 4 is just too high. And so if you were to lower that, the really even on cloud environments, the recommendation is to lower that to something like 1.1 or 1.2. Now, sequential page costs is 1.0. And so you probably don't want it to be equal to sequential cost, but making it closer to it means that Postgres is more likely to select your index. So this is something I wanted to put out there as one first quick way to understand an impact that a setting in Postgres has on using these new indexes, as you might be excited about starting to try to use them. So that's the quick overview, and it was a little bit more than 30 minutes of just what indexes are available, some of their quick use cases, even how some of them actually are implemented. And then, this is the time to start to understand, when they can be useful for you and how you can go find more information. The documentation, there's tons of good documentation about every single index, how they're implemented, the kind of operators you can use with them, how to, the operator that's necessary if you want to use it, something like that trigram operator that I showed. So please check out the Postgres documentation. And again, that's the beginning. So if you have questions, I'll look and see what the team has, if questions have come up. But please throw them in. There are a couple of things to share with you. So if you registered for this webinar, 3 people we selected at random to go ahead and win a ticket to Past Data Summit in November in Seattle. So I'm going to give you that in just a minute, as questions may or may not come in. The other thing to tell you is that our next webinar in the series, we're going to talk about these unique data types. So now that we've talked about how you can index them, we're going to talk about all the data types in Postgres, what they could be used for, and even how you can create your own data types. That will be in October, on October 8th. Again, you can sign up for that at the Redgate website, and you will get reminders of that, I'm sure, by attending this webinar. Just to remind you as well that we have this series that we are continuing. So go catch up on the old ones. This recording will be made available soon. So we do have at least one about a hash index. And it says, in that case, can a hash index miss a value or record? No. So it will always return. So there are different hashing algorithms for each data type. I didn't get into that, but they are implemented. And so again, if you create new data types, you can create hashing algorithms. It will always return a value. And that value will go to a bucket. And again, we're pointing to a row pointer. And that row pointer may or may not be the exact value it will be the exact value that that was hashed. It will point to that row, but because multiple values could point to the same bucket, we pull all those rows off. And as we read the rows, we just verify that the row actually matches the value that you are looking for. That's why it's equality only. But you won't miss a value. You will always get at least something out of the hashing algorithm. It's a guarantee. Otherwise, you get an error if for some reason that Postgres can't hash that thing. And again, like I said, so every data type has a hashing algorithm by default that's provided with Postgres. And so you will be guaranteed to get something out. Hopefully that's helpful. And there's some nuances there. I'm not going to say that hashing algorithm is perfect. Like anything else, you might want to reindex over time, just as things might move or as the index itself might become a little bit bloated. And that is one thing I should add, and I will remember to go do that afterwards with Brin indexes. So thank you, whoever asked this. Brin indexes, that is the one caveat to Brin indexes. They are maintained over time. However, if I have that 128 block, I'm going to scan back here really quickly. I have this 128 pages, and right now that reference in the index says that in this grouping of 128 pages, the low value is 0 and the high value is 50. Well, if a value on one of those pages is changed, and now the high value might be 75, that index is no longer correct. It will get cleaned up quickly, just not immediately. And so there are times where you might read more pages than necessary, but then it's still going to recheck every row coming off of that, off those pages to find the values that are needed. And so again, this is something that's been improved over and over as new versions of Postgres have come out. It is one small thing to be aware, and that's why block range indexes are really most valuable for increasing data, incrementing data that is not going to change frequently. But it's just a little nuance, something you need to know. And now, last 2 things. Any other questions? You have a minute. Otherwise, let's get to these. And so that is the state of the database landscape. We still have 3 weeks to fill this out. This is something that Redgate has done in some form or fashion for the last couple of years. Last year, it was a more expanded survey dealing with what it looks like inside of your organization. how many databases, how are you using them, the practices for managing them. Really, really valuable information. You can find the results from last year's survey online. And this year, we are starting it again. You can fill it out until September 30th. And you simply go to rd.gt/survey24, and you'll get a reminder of that in the email, and you can find it through the RedGate website. If you fill it out, you will have a chance to win. I believe it's one of two $250 Amazon vouchers. And last year we had almost 4,000 people fill out the survey. We would love to see more than that. Again, if you look at the results, I think you'll agree that there's a lot of really valuable information that came from that. And so please consider filling that out and joining your fellow data professionals. So am I available? I guess there's a question. Am I available for corporate data training, corporate training on Postgres? RedGate has a lot of ways that we like to support the community. And so, certainly reach out to RedGate, particularly if you're a client. There's some new things we're exploring for doing actually things like that. You can reach out to me directly. I can point you to some things we're doing here internally at RedGate and some other options that I can help you with. But yeah, reach out to me, reach out to, if you happen to be a RedGate client, to your account executive. They'll be happy to help you out. I love doing this kind of training and helping people learn Postgres. And so it's something we're trying to figure out how to do more of. So thanks for asking. That's great. And one last question before I get to the big announcement of who won these, who won the tickets. Finding the best index. Is it possible that there's a cost to running a few different indexes at once? Oh, really, really interesting. So Postgres, if you can index the same column with multiple types. So I could have a B-tree index on a date column, and that might be really valuable when it is valuable when I need to use something other than equal. However, if I know I have incrementing date ranges, a Brin index is really efficient. And if I need to find pages that have an exact date, that's a really efficient way to do the search, and it's much smaller. So Postgres might use that index for an equality operator. But if you say greater than today or greater than yesterday, it will use the B-tree index, for instance. And so, yes, you can have them. There is a cost. Every index you add is a cost to when you add data, or you reindex, or you modify data. But depending on the index, it's honestly probably negligible if you know that you're going to get the value ultimately out of it. Testing goes a long way. I will say this, trigrams, for instance, I have used them in the past. They're very, very beneficial, but they are a pretty heavy index. Think about it. You're storing a string 3 characters at a time over and over again. So the first 3, and then the second, third, and fourth, and third, fourth, and fifth, and so forth, including spaces. And so that takes a lot of effort to actually create, and it actually creates more storage. The end result can be really, really powerful in large tables when you're trying to do that in the middle of a word search. There's similarity searches and so forth. It can be really, really powerful if it suits your use case. So great questions. Don't hesitate to reach out with more. Again, my contact information, I could go back to, but it's just Ryan Booz, all one word, on socials, and my email address. It's easy to get a hold of me through LinkedIn and so forth for here at RedGate. And now the big news. Who won the 3 Past Data Summit? These are the 3-day tickets. So Wednesday, the main conference, Wednesday, Thursday, and Friday in Seattle, November 4th to the 8th. I'm going to be there. Grant, Steve, we're all going to be there. Lots of excellent, excellent talks on the docket for those 3 days. If you can make it, this would be a really great experience for you. So the team will reach out to you if you have won. I'm about to announce this through email, and you can discuss what that looks like. So here we go. The first is William Diagicamo. So William, congratulations. The team will reach out to you tomorrow. The second is Matej Hekech. And number 3 is Hampus Ludvigsen. So William, Matej, and Hampus, great job. Thank you so much for registering for this webinar. Hopefully you learned something new and valuable about Postgres. And again, the team will reach out to you, and I hope that you can make it to Past Summit this year. Thank you, everybody, for being a part of this webinar today. Please check out our resources, register for the next one, and reach out with anything you need. We're so thankful you're here. Take care.